So for Hilbert space, we talked about the completeness, which means that like does the space, is it like completely filled? So if you look at this example, like if it ranges from 0 to 1, but if it doesn't include, that is not incomplete. So for example, when as x approaches infinity, 1 minus 1 over x will approach 1, but it won't be exactly 1. So this is incomplete at the place of 1. And a normed linear space is complete if ever Cauchy sequence is a convergent sequence that is for energy sequence, for. So this makes no sense to me, but what it is that, you know, if you look at this kind of function, like it kind of goes to, converges to like this, like one point as it like goes to infinity, where, so this m and n, which is just a sequence or the index of a whatever it is, so the arbitrary, and it's like going to infinity, so in like they're like one apart or like really close to each other. So so let's say it is like m is here and n is here or something like that. The distance between them is, or the value between them is like this minus this. So there's a pretty big, you know, difference. But if you go to like here, where m and n are like far beyond, closer like to infinity, or the difference is going to be minuscule and it's going to approach 0. And so this will be, and this point, so the limit, this converging point of this value will be included in this vector space as. So the limit will exist in the vector space if they look like this. Or if this is the case, this limit, it is existing in subspace or the vector space. And talk about this Banach place and Hilbert space. So Banach space is the normed linear space that is complete. So norm is like, you know, the length of the vector. So whereas Hilbert is inner product space, which includes not only the length but also angle. Think of a dot product. Dot product is kind of, if you have this two vector ish, and it's like the projection to one another, so it would be like that. Oops. So it would be just like here, and so it includes not only the length of this vector, but also tells about the angle between them. Because it would be orthogonal, it'd be like, or closer to being orthogonal, the length will be even smaller too. And as they're like more aligned and more aligned, the length is getting longer. So it tells about not only the length of the vector, but also the angle. So Hilbert space contains more information than Banach, and because of that, Banach, all Hilbert space is Banach, I guess. So it only requires length, but Hilbert also requires angle. And then approximation function in Hilbert space. So what this is like all is saying is that so if you think of a room and let the Hilbert space be room, and we're gonna have this like a paper in some 2D paper, this kind of paper, in this like room, and we have some point in the room, let's say just this like tip of this tumbler, that's the x, and there's going to be a point in this paper T that is closest to this point of our interest. We're going to call the point on the paper this hat x, I guess. And okay, so let's say this hat x, actually I'm gonna, okay, I denote it with hat x, and it's gonna be orthogonal to this point of our interest, as in like 90 degree. And there's only one point that is closest to it. And all the other points in this paper is farther from this point of our interest. So that's what this is basically saying. And so proof of this, so let x be the vector that satisfied, so this e hat is the vector that satisfied this, so it's a distance between this point of interest, and then that point from here, which just happens to be orthogonal in the subspace. And any other vector, it could be anywhere on this paper, and let's say this point to this point, and we were like that. But anyway, so if that's the regular E, we can prove that this distance is not the shortest distance, is always greater than the shortest distance, which is from the distance between from the orthogonal place point to here. Anyway, if you do that, if you do like some math, and you can prove that is the case.